This is embarrassing.
Okay, you guys, here's the week ahead. Again, just a section a day. A lot like last Friday, 15.4 is a pretty quick section. It introduces the notion of computing surface area using a double integral. And what I'm going to do is I'm just going to run through that material pretty quickly. It's going to take perhaps 15 minutes. And then I decided that we would do some review of what we've done so far, mostly cylindrical and Cartesian coordinates, integrals in those coordinate systems. So we'll be working in groups. When we break up into groups, I want you to just sort of work on setting these up and not so much on doing the integrals at this point. That doesn't mean that it's not important to be able to do the integrals, but for the purposes of class today, I'd like to discuss as many of these as possible in terms of setup. So that's the goal for the day. That said, before I go there, are there questions about the homework that you've been working on and are going to hand in right now? Yeah, go ahead, Chris.
I had issues on the first one getting 2a cubed over 3. I got 2a cubed over 2, and I just can't figure out what I did.
I may not be able to drill down that far in here, but let me.
I could always need to do that.
Well, let me just let's look at the problem though and see what we're talking about here. And really, the network again?
Oh, and another question: when it refers to the first octant,
yes.
are we talking about the region x, y, z all greater than 1?
All greater than 0.
Oh, that's what I meant.
Mm-hmm. Yeah, and it's not something, I don't know if it's explicitly mentioned in the book, but it's if you think about three-dimensional space, and there are these 4 octants above the xy plane and 4 octants below the xy plane, and the one where everything's positive is called the first octant. And frankly, I don't know what the other ones are called. I don't know how they're numbered. I could probably guess, but not something I memorized. So what problem was it?
I'm talking about the star problem.
Oh, went through all that.
Maybe, yeah. Maybe I just set up my limits wrong. From 0 to a on both.
So which problem?
Oh, okay.
Did you figure it out?
Yeah.
Okay, moving right along then. Other questions?
Number 3 on the web work.
3 on web work.
The different point masses.
Yeah, I wasn't sure how much you guys had done this stuff in Calc 2, but this problem is an homage to what we're doing right now with center of mass, and so I thought it was worth looking at. Let me show you what I mean by that. So we've got these 3 points. Let me try to sketch them out here without. Okay, and we've got negative 5, 3. 1, 2, 3, 4, 5. 1, 2, 3. Negative 3, negative 2, and then I don't remember what the other one was. Negative 3, negative 1. And 3 masses, I think this was 1, this was 8, and this was 9. So you'll remember when I talked about this last time, I talked about gravity acting into the board and wondering, how much does this point right here want to rotate the y-axis? Or how much does this point want to rotate the x-axis? Vaguely, you remember that? Okay. So you can actually figure that out for point masses pretty easily. So my is how much these points want to rotate the y-axis. I better label that. How much does this mass of 1 kilogram or whatever want to rotate the y-axis? It's simply the mass times the distance from the y-axis. And so this thing is 1, 2, 3, 4, 5, negative 5. And then what about the others? So then there's an 8 times negative 3, and then there's a 9 times negative 3. And, sorry? And if you add all these guys up, what you're going to get is the net tendency for these weights to twist the y-axis. And that's why I kept the signs in there, the negative signs in there, because that's going to tell me that it wants to twist it in a particular way. Mx is how much these masses want to twist the x-axis. So let's go through this again. You have the mass times the distance from the x-axis, in this case positive 3, plus 8 times negative 2, plus 9 times negative 1. That's the moment about the x-axis. So once you see the process, I think. Now, how is this an homage to the double integral formulas for mx and my? Well, let me remind you what they look like, first of all. X times sigma x y dA. Think about what this is. Sigma is the density function, dA is a little piece of area, so sigma times dA is a little piece of what? It's a little piece of mass. And x tells me what about that little piece of mass? How far from the y-axis it is. And then this integral essentially sums that all up with respect to the y-axis. If I instead take this and put a y here, then what I'm getting is how much the figure wants to rotate the x-axis. And you can see this direct connection between mass times distance from the axis, adding them up. There's mass times distance from the y-axis and adding it up. It's not super deep. Other questions? So it's really just a matter of did you know how to do it than anything super deep.
Just on that, the linear relationship between distance and force exerted, like the torque, that's experimentally determined. That's not that's based on physics.
Yeah, it's based on physics, and it's not experimental. You can get it from first principles, using Newton's law and that sort of stuff. Okay, other questions? Tabo.
You saw how to set up start problem number 11 according to the leaf.
Okay, so my big advice for this that you may have seen is to actually plot this thing using the techniques that I showed you, gosh, I guess it was last Wednesday. So get yourself some polar graph paper and plot this thing. And I think if you plot it, as you go through the process of plotting this thing, you'll get a sense for what these limits of integration should look like. Okay? Did you do that, Tabo, yet? Have you had a chance to do that?
I didn't do it on the polar paper, I just did it on the paper.
So, and so what limits of, the thing you want to focus on when you're plotting this thing is, to me anyway, is a combination of the important angles. So let's look at cosine 3 theta. For example, when theta is equal to 0, what's the cosine of 3 theta? It's 1. So let's just put that out here somewhere. Now, as you go and you increase theta in this direction, when's the first time that it's going to hit 0? For what angle theta is cosine 3 theta going to be 0? Pi over 6. So if I get out to an angle pi over 6, and let me sketch that in there, this guy is going to sort of just flow into 0 there. And you can see that as I start at 0 and I go positive, I get the upper half of this row of this leaf. How do I get the lower half? Just start going negative from 0. So if I go negative from 0, there's negative pi over 6, and that's going to flow out of this point and kind of head down to 0 right along that angle. And there's a leaf. Now remember what I said when you're trying to build limits of integration for a polar region? You build it out of what? Rays and angles, right? Rays and angles. So let's look at a ray here. There's a ray. There's a ray. As I'm building these rays, the rays always go from where to where? 0 to cosine 3 theta. And then from your plotting exercise, you recognize that one leaf, bless you, one leaf is covered by this range of thetas.
Isn't it easier to do it just from 0 to pi over 6?
Yeah, you could multiply it by 2, sure. And then if I'm trying to compute the area, what's the integrand? It's just 1, right? And then the dA is r d theta. Okay. Other questions? Okay, then let me talk briefly about surface area. I do kind of like the setup of this chapter where we introduce Cartesian coordinates, polar coordinates, and those integrals. And then we do just a couple of very short sections of specific applications, in particular center of mass problems and now surface area problems. Really, these are just slim covers for doing more double integral problems, which is really what we're about here, is being able to build these double integrals, because when we get to the next chapter and I start showing you these beautiful theorems that I keep promising, I don't want us to have to worry about, oh, how do I build this double integral, or how do I build this triple integral? I want that to be automatic. And these two sections in particular are just really helping us get a little more practice with these kinds of integrals. So I'm going to switch over here to make it easier for me to write. It's all about me. There we go. Almost there. I can be patient. All right, surface area. So I'm interested in a very specific example of surface area. That is, the surface area of a surface of the form z equals f of xy above a region R in the xy plane. Let me just sort of sketch that out a little bit, because I want to motivate this formula that I'm about to give you. So here's some surface. That's described by the equation z equals f of xy. So not all surfaces can be represented this way, as we've discussed earlier. What's an example of a surface that can't be represented this way?
Anything that's not a function?
Anything that's not a function. So the sphere is a classic example, right? You can represent the upper half of the sphere using a function like this, but you can't represent the whole sphere using a representation like this, because the sphere doesn't pass the vertical line test. Okay? Okay. I certainly do not. How about just the red X? Yeah. Okay. So let's think about, we actually have the tools to try to get a grip on this surface area. All right, I want to think about two curves, two cross sections here. One is a cross section in the y direction, and the other is a cross section in the x direction. And I want to think about little tangent vectors along those two lines. Earlier in the book, we noted that these tangent vectors can be written as follows: 0, 1, f sub y, and this guy can be written as 1, 0, f sub x. So earlier in I want to say chapter 13, perhaps, 14 probably, we noted that this was the case. And I want to scale these guys down by little infinitesimal distances. Let's say delta x here and delta y here. So now maybe they're really tiny little vectors, like that and like that. And I want to think about the little parallelogram that those guys define on the surface. And we actually have a way of finding the area of that parallelogram. I don't know if you guys remember or not. Not quite. It involved, it was from chapter 12, actually, before we did any calculus at all. Cross product, yeah, exactly. Good memory. Particularly impressive because we haven't actually talked about that since chapter 12. Okay, so the area of the little parallelogram is just the magnitude of the cross product of these two vectors. Like that. So let's compute that cross product inside the magnitude here. Cross product, it doesn't really matter which order we go. So let me just write it out for you. So if you do the cross product, you'll get a third vector, minus fx minus fy, 1. And remember, f sub x is the partial with respect to x, f sub y is partial with respect to y, etc. The magnitude of that vector is just delta x, delta y, f sub x squared plus f sub y squared plus 1, all square root. So that represents the area of one of these tiny little parallelograms. If I want to get the area of the whole surface, guess what? I mean, what am I going to do with these little pieces? I want to add them up. And the typical way to do that is with an integral. I'm going to put dA here, but what I really mean is dx dy or dy dx. Okay, I use dA so that I'm not imposing a particular order of integration on you. The delta x, delta y turn into a dx dy, and effectively speaking, turn into a little dA. Somewhat reminiscent of the arc length formula. To that end, the WebWork problems, the book problems are all sort of carefully designed so that these integrals don't blow up in your face and become impossible. So if you're doing these integrals and they're getting kind of crazy algebraically, possibly you're not thinking about it right, or maybe you did your partial derivative wrong or something like that. So just keep an eye on that. Just the tip is that these integrals should work out, even though in the real world they tend to explode all over the place. Let's do an example. So let's use this approach to confirm that the surface area of a sphere of radius capital R is 4 pi r squared. Now, I just got finished mentioning that this was a case where this formula doesn't work for the sphere, but it's actually a manageable hurdle. So it doesn't work for the sphere. The sphere can't be written as z equals f of xy, but how can we overcome that hurdle in this particular problem? We could compute the surface area of the upper hemisphere and just multiply by 2. So that's what we'll do instead. Okay, so what's the equation of the upper hemisphere? Well, if you take x squared plus y squared plus z squared equals capital R squared and solve for z, that's r squared minus x squared minus y squared. That's the equation of upper hemisphere. Right?
Is that S delta?
That's SA. Where is it? Yes, SA, surface area. So to apply this formula, we need f of x, f sub y. Let's do that, f sub x. Lots of chain rule here, etc. 1/2 r squared minus x squared minus y squared times, by the chain rule, negative 2x, which simplifies to negative x. Simplifies to that, right? So there's a 1, oh yeah, to the negative 1/2. Thank you. Oh, yes, to the negative 1/2. All right, so does everybody see that? And by the massive amounts of symmetry in this problem, this is also true. So what do I do with f of x and f, or f sub x and f sub y? I shove them into that surface area formula. So let's look at that. All right, so f sub x squared. F sub y squared. And the 1 goes along for the ride, and there's a square root. Yeah? This actually simplifies. You might not realize it, but this simplifies quite a lot. So where did that nasty fraction at the end come from?
It's 1.
It's just 1. I'm just finding common denominators. So these guys already had a common denominator, so I added them together. And I took 1 and I re-expressed it like that, so that now I have another common denominator. What happens when I add these two guys together? The x squareds and the y squareds cancel. And, oh, was there something I could press?
It was like keep disgusting and don't ask again.
Thank you. I don't like to read pop-ups when I'm teaching, but it's probably worth doing it. Yeah. So thank you. The last thing you want to do is like say yes or something. So usually I just like to hit the red X. All All right, so continuing in a non-technical fashion here. So yeah, nice simplification happens there, and I can finish this off and make it look a heck of a lot like where we started. Like that. What do I do with this expression now that I've simplified it as much as I can? I need to integrate this thing, right? Okay, I need to integrate this over the region below the hemisphere in the xy plane. Well, what does that look like? So what is the region below the hemisphere in the xy plane? Nick? Of radius r. So if I take a sphere of radius r, centered at the origin, and I look at where it intersects the xy plane, that's a circle of radius r, centered at the origin. Absolutely. Okay, we're getting there. So that means I need to integrate over this region. I'm going to call this region D because r is already taken. Now, I could just plow ahead here and use Cartesian coordinates, but this problem is actually well suited to polar coordinates. So why don't we just take advantage of that fact and change this over to polar coordinates. So let's use polar. If we're going to use polar, how is the region D described in polar coordinates? R goes from what to what? 0 to big R, right? You definitely want to keep track of your little r's and your big R's. And theta clearly goes around the circle. The integrand. How does the integrand change in particular? What's the denominator going to look like?
Square root of big R squared minus
Square root of big R squared minus little r squared. Good. And dA becomes r dr d theta. Yep. Is that a doable integral? Yeah, it's not bad. Right, there's a u substitution here. We'll let u be this, and we've got a ready-made du sitting out there. If you do this integral, just for the sake of time, I'm going to leave that to your capable hands. If you do this integral, what you'll end up with is 2 pi. In fact, let me throw in an intermediate step. This thing here is independent of theta, right? So I can do the theta integration, and what's that going to give me? Just a 2 pi, right? So without doing any work at all, really, in terms of integration, I can take what appears to be a pretty complicated double integral, and I can take this constant r out of the r integration. And when I do the theta integration, I introduce a 2 pi. And what's left behind is somewhat cleaner integral. You still have to do some work. It's still a u substitution problem. If you work that integral out, it works out to 2 pi r times r. 2 pi r squared. Not 4 pi r squared, but that's what we expect, right? Because this is only the upper hemisphere. Okay, so full sphere. Multiply by 2. and we get 4 pi r squared, which is pretty much what we expected. Okay. There are more problems like this at the end of the section, and in the web work, again, it's really just more applications of double integrals. So now you have this nifty formula that gives you surface area. You still have to identify regions of integration. You still have to identify surfaces, etc. Questions about that? Okay, so let's say for a half hour or so, we'll work on in groups on these problems. And again, I emphasize I'd like you to set these up, but not do the integrals. Let me see if I can pause this thing somehow.